Okay, so we need to make sure that we are careful with our limits of integration and our notation just in general. The way this relates back to partial derivatives, so thinking about partial derivative, we start off with the function, and we'll just work with a two-variable function, something in terms of x and y equaling z. We know we can find the partial derivatives. That's not something we're going to go back and review right now. We've talked about that plenty. But when we find the partial derivative with respect to x, what do we basically think of y as?
Constant.
Yeah, we pretend y is a constant. So we treat y as a constant.
Good job.
And then this backward thing happens if we're doing partial respect to y. We go back and treat x as a constant.
Oh, these were fun.
And so when we're trying to undo this process, which is what integration does, it undoes derivatives, we need a way to kind of undo both these pieces together to get back to that original function undo. We need a way to undo this to get back to the original function that we started off with there. So instead of taking a function and taking the derivative in pieces, we're going to have to take these pieces and kind of put them back together to make this original function here, is what we're going to go for there. But the idea of treating one variable as a constant and the other one as a variable is still going to play here. We're still that same idea when we're working with this. If we're doing a problem in terms of y, so as a dy problem, y is the variable, which means any other letter we see there is when we treat it as a constant. And then we bump out to the next one. So when we do as a dx problem, now x is the variable. Again, anything else that shows up there is going to be treated as a constant. So a lot of similar ideas here. We're just working backwards for undoing that. Before we get to that part down there, just kind of like side note here. So for example, let's say that we knew the partial derivative with respect to x of some function was 2xy. What possible function could we have started off with to get to this point?
Probably like
X squared y.
squared y.
Yeah, if we had x squared y and took the partial with respect to x, we would get 2xy. Is that the only function this would work with? What if I had like plus y squared over here? Would that still have the same partial with respect to x?
Yeah.
Yeah, because the derivative of y squared is going to be 0. If I had some other just straight up constant over here, it's still going to be the same thing. So we've got a lot of options for what can be here. I mean, this y squared could be something much more complicated. We can have natural logs involved. We can have trig functions. I should say y. We can have trig functions involved. We really don't know what happened to that y piece because that partial just doesn't tell us, which is why we have to kind of do both these pieces. We have to account for the partial respect to x and the partial respect to y. Okay? But the process is when we're going to go back and undo this, when we're going to basically find the integral of this with respect to x, we're going to have to think about ways to account for that. We'll talk about that in just a minute. So in general, what that's going to lead to is this. If we take the partial derivative with respect to x, and we try to undo that, we have to undo that still with respect to x there. So partial respect to x, undo that with respect to x. And it will take us back to part of the original function, but it's going to be missing those y components. If we didn't have limits of integration here, we could just add some constant that was in terms of y. But with those limits of integration, I'm going to write this a little differently here. Erase all that. Okay, we can still go back and use the fundamental calculus just like we've done before. We're going to go back and evaluate it from upper limit to lower limit, just like we've done before. And these guys are still constants in terms of x. Okay, because when we're doing this problem, we said dx, x was the variable, everything else is basically a constant, so we're plugging in some constants there. And depending on what those limits are, we may have y involved, we may not have a y involved, just kind of depends. Okay, and then similar down here, if we go back and do this, we are going to get some version of the function. But now we're talking about integrating with respect to y. And so similar thing, that g1 and g2, they are constants in terms of y, even though they might have an x involved in them. We're going to do an example in just a minute. But any questions so far? Does this seem like it makes sense, at least what we're looking for?
Yeah.
Okay, well, let's do an example, and then hopefully you still agree with that or have a more confident sounding yeah. All right, example 1 on page 2, we are going to integrate. We have just one integral right now. This is most just that concept of one variable being a constant, one variable being a variable itself, and just working through it here. And then example 2, kind of put it all together. So if we have the integral from 0 to x of x plus 2y with respect to y, what is the variable we're working with right now? Yeah, someone said y. Okay, we are doing a dy problem, so y is the variable. If we're thinking about this in terms of what this means, we'll get to that later, but now that y is what's changing, so those y values are getting smaller and smaller and smaller and smaller. That's the change with direction in terminal. So integrated, what is the antiderivative of x with respect to y?
1/2 x squared.
Nope, that would be with respect to x. Pretend x is a constant. Pretend you said like 7. If you had the
X squared.
X squared. Okay, because x is just some constant. We don't know what it is, but in terms of y, x is no longer a variable at this point. It's just some other number there, so xy. And then for the second term, because all the sum and difference, all those rules still apply here, still integration. What's the antiderivative of 2y with respect to y?
Y squared.
Yeah, there we go. There's y squared. Okay. Fundamental theorem of calculus still applies, so we're still going to go back and evaluate this from 0 to x. There we go. But that would be the antiderivative part. Much like when we did partial derivatives, there's really no new rules here. All the same integration rules that you learned back in Calc 1 and Calc 2 still apply. We just have to be able to keep straight what's the variable and what's the constant. And so since it's a dy problem, y is the variable, and just pretend x is some other number. And that also means we're going back and doing this substitution here. Are we going to replace this 0 and this x in terms of x, or are we going to replace it for y? We're going to replace it for y. Y is still the variable. We're still going to go back and plug all this stuff in terms of y. And I will tell you, for me, this is the part that I mess up with the most. So if you notice a mistake, which you guys are good at telling me when you notice them, let me know. But we are going to go back and plug all these numbers in for y, since y is the variable that we are working with here. Okay, so that x is just going to stay there. So here we go. We've got x times x plus x squared. So that's what we'll go back and plug in the upper limit. And then subtract x times 0 plus 0 squared. All right, so it's been a while since you integrated. Remember, top value plugged into the function first and minus the bottom value plugged into the function. They're going to simplify. Okay, so if we reduce this down, x times x is x squared plus x squared. That first bracket gives us 2x squared. And that second bracket just all reduces to 0, so just 2x squared. And there we go. Not an iterated integral, but just that idea of keeping one of the variables constant. Our brains are very used to working with x as a variable, and we've got to kind of break that pattern. Questions? All right, let's do an iterated integral then. So this is an iterated integral because we've got 2 times that we are integrating. And usually these brackets aren't going to be there. Okay, they're there this first time right now just to kind of remind us that we're grouping things. We're still finding order of operations to the inside part first. But if you look ahead in the notes, those are not usually written there. Those are just for this time. But anyway, we're going to work between the inside out. We're going to do the first integral, and then after we get that thing whole entire finished, we're going to go out and do the second integral. If there is a third one, we'll just keep going. So always working from the inside and going out there. And you can just pay attention to notation. So if we do that very inside integral first, so this one right here, what is the variable for this integral? Yeah, a lot of people are muted, so I can tell you're saying y. So it's y again. So very similar to what we did last time, we're going to go back and integrate that. So we still have that outer integral. So from 1 to 2, and then I'm going to leave a bunch of room for my work, and then dx, all that stuff is still there on the outside. We are just working with what's happening on the inside there. So here we go. What is the antiderivative of 2x squared times y to the negative 2 with respect to y?
You have to be asking, am I okay?
So what's the antiderivative of that first piece with respect to y?
1/3, right?
No, 2 is a constant, right? So it just hangs around. X squared is a constant, so it just hangs around. Really just integrating the y to the negative 2. So it'll be like y to the negative 1 over negative 1, or negative 1 over y would be okay too. So again, 2 is just a constant, x squared is just a constant. We are really just integrating the y to the negative 2 term. So then similarly, what's going to be happening for the next term? Instead of 2y, we'll have
y squared.
Y squared. Okay. This all has to be evaluated from 1 to x, since those are those inner limits. And I left way more room than I needed to. So I'm going to scoot that dx over just so it doesn't look as torquey. There we go. That looks a little better. And that is the most confusing, well, one of the most confusing parts is remember that we are only integrating with respect to y x has to be treated as a constant. So the more you practice it, just like with partials, you guys have gotten good at that. The more you practice it, the easier it'll be to kind of keep track of what's going on in your head there. But very similar with different partial derivatives. All right.
Stop it. Why are you laughing? Because you're making me laugh.
All right, so if we go back and do that substitution, again, just replacing for y, we're going to have 2x squared times, I'm going to flip that around so it looks better. So negative 1 over x plus x squared. And then we're going to subtract by plug in a 1.
Oh, never mind, never mind.
Okay.
See, I'm not the one that's questions. Because you never mind.
Pen is really being bad today. I'm sorry. I know everything's all choppy and stuff. Okay, does that work? I don't think I goofed anything here. I think I'm okay so far. So the x's stay there. They're just constants. We're replacing all the y's with whatever the limits are, which is x for the upper limit and 1 for lower limit. So reduce that, and then now we are left with just a good old-fashioned integration problem here. And I will just, for the sake of time, I know you guys know how to do algebra, so instead of going through the steps here, if you reduce this down, eventually we can get integral from 1 to 2, and then all that middle stuff is going to simplify down to 3x squared minus 2x minus 1. So instead of going through and actually combining all like terms there, that's what you would get. But then once we're here, I mean, this is familiar. This is something that Calc 1 students can do without any trouble. So just be careful with the arithmetic and you should be fine. So we're going to have x cubed minus x squared minus x, evaluated from 1 to 2. So that is 8 minus 4 minus 1. Oh, sorry, minus 2. And we plug in a 1, we'll have 1 minus 1 minus 1. So 8 minus 4 minus 2 is 2. 2 minus negative 1 to 2 plus 1, so that gives us 3. And we're not talking all about the meaning of this yet. Meaning will come later on as we work through different sections. Right now, this is just going through the process. So it's like the algebra, just the arithmetic. Questions?
I think Brian has a question. Brian, have a question?
Do you have a question?
He's asking, how do you get 3?
Like when you multiply 2x squared times negative 1 over x, wouldn't that be negative 2x? Oh, you got.
Yes, it should be a negative 3. Is that what I goofed on?
Maybe.
Oh, no. Because over here, I did a lot of simplifying. I skipped it. So this is going to reduce down there.
Yeah, so it's negative 2x.
And so that's where that negative 2x comes from. And then when we combine this term and this term is where the 3x squared comes from.
But where'd you get the x squared from?
From right here. So the x squared just kind of hangs around because it's constant, so it's still just there because it's a constant. And I rewrote this. So if we have y, the negative 1 over negative 1, that looks really busy. But that should just be the same thing as negative 1 over y. And so that's what's happening here. I rewrote it. I flipped it around without actually showing the work for it.
Okay.
So all the y's got replaced with whatever limits were of integration, which is why the y is not there anymore. Now it's going to be 1 over x. And then instead of y squared, we're going to have that x squared on that second piece.
Yeah, I got it.
Does that make a little more sense where the parts come from?
Yeah.
Okay. Other questions on that one?
Hey. Yeah.
I think the homework for this one is posted. So this weekend, theoretically, you should be able to work on it because I know you want to work on that and study for a test. But if you need to practice there, you'll be able to early next week go back and work on it. There it should be up. Okay, a couple things to note here. I've mentioned briefly what an iterated integral is, but just give it a little bit more of a definition. What we've said so far is an iterated integral means that the integrand has an integral. Someone's trying to get into my classroom. Hi there.
Hi, I'm sorry.
That's okay.
The faculty needed all this.
Okay, they can't have this one. It's not teaching class. That's why I locked the door. They wouldn't try to come in. Okay. So iterate integral, the integrand is an integral, so that's why it's kind of nested there. The other important piece now, which really doesn't make any sense to us because all we've seen it, but the other important piece is the order of integration is given. And that will make more sense in the next section. Like dy dx or dx dy, we're told what the order of integration is, which seems obvious because you can't integrate it if you weren't told that. Like I said, the next section will make more sense. So put it in now while we're defining it, and later on that second part will make a little more sense. But the other thing is, and this is going to apply for any iterated integral we ever work with, is your inner limits, whether you have 3 integrals or just 2 integrals, your inner limits of integration are always going to be the most complicated. So in the example we just did, we had a 1 and we had an x. X is a lot more complicated than just a number. I mean, it represents something that can change there. Sometimes we're going to see we have whole functions put in there for limits of integration that involve multiple sums or differences there. So they can get a lot more complicated. But they are still going to be considered constants in terms of the variable we're integrating with respect to. And as we work with the problems more, hope that makes more sense too. But they're the more complicated ones. They could have x, they could have y, depending on what the first variable we're going to work with is. But it's still treated like a constant. Okay. The outside limits of integration, so the very last ones we do, these are always going to be constants. Good old-fashioned numbers most of the time. Okay, very rarely will we see those containing any variables whatsoever. They're almost always just numbers, just scalars. And again, we'll work with this more, and those ideas will kind of keep showing up there. Before we get too far into any kind of meaning behind this, there's one more little piece to kind of be aware of here. The limits of integration aren't just following this pattern of more complicated on the inside, less complicated on the outside. They also tell us what we are integrating over. So think about in just a one variable case like this. Actually, let's even go something simpler. Just note this on the bottom here. So let's say we have this function here. We're going from 1 to 2 of just x squared dx. Okay. Hopefully you recognize that you can graph this thing, and we're finding area. So x squared looks kind of like this. What do those limits of integration from 1 to 2 mean? What do they tell me? So how do I do anything with these limits of integration? How do they relate to this picture?
They tell you the slope,
The area?
We're finding the area, an area between what values of x?
Negative infinity to infinity.
Nope. What do those limits of integration mean? If we are doing a regular single integral, and we've got limits of integration from 1 to 2, what does that 1 to 2 mean?
Are those the bounds?
They are the bounds, yes, they are the bounds. So we are talking about in terms of x, so on this x-axis, those are the boundaries. We are just looking at this little portion of that graph. So wherever our graph is during those bounds, that is the only part of this graph we are really caring about. The rest of this graph is essentially useless for this problem. We're just not using it. Okay? We do know we can interpret this as area. That is totally true, and that's not changing. But keep in mind, those boundaries that from 1 to 2, they have meaning. They're telling us what part of my x-axis am I looking at. That's the only variable I'm working with respect to. Where is the function over that region there? So if we try to see how when we add more integrals, this changes our limits of integration. So we'll go back and use this example here. Okay? If we think about how this affects things, not only do we need to know that we're going from 1 to 2 and from 1 to x, we also have to know what variables we're doing this with respect to here. So top of the next page, we'll take a look at that. So if I just copy those boundaries from example 2, we were going from 1 to 2 and from 1 to x. I don't really care what the inside is. Ignore that right now. And then the order of integration we're given was dy dx. Okay, so ignoring all the inside stuff in that example we just did, these are those boundaries that we have. Okay. Well, we're working with 2 variables now. We have x and we have y. We know we can graph 2 variables on a good old-fashioned coordinate plane. So let's try to make sense of this. our first limits, the inner limits right now, are all in terms of y. That inside integral is a dy problem. So what these limits are doing is telling me the changes in terms of y. If we think about this as just a function, y equals -1. What does y equal -1 look like on a graph?
Did you say y equals -1?
Or a positive 1. What does y equal +1 look like? Caleb, horizontal line, right? If we go back and do the same thing for this, we say, okay, well, if y equals x, what does that look like?
A diagonal line.
Right, yeah, so your identity line just goes through like this. Okay? That's what those limits of integration mean. On their own, they're pretty useless. Okay, those two crossing lines really don't tell me a whole lot right now, but that's what those limits of integration mean. We're saying y is my variable. If I think about y equaling this lower limit, I'm going to get one boundary. If y equals this upper limit, I'm going to get another boundary. And put together with what we're going to look at in just a second here, we're going to create this region of integration. So if we do a similar thing for the dx part of this, if we go back and let x equal 1, what does that look like?
It's a straight line.
Yeah, it's a vertical line, and right here is where 1 is, so it's going to intersect right there. If we do the same thing on the top, let x equal 2, we also get a little vertical line, just scoot it over a little bit. And these things together are going to cut off this little region right here, right?
Yeah.
And so what we're doing with these limits of integration is we're basically building this little triangle. We're saying, okay, here is the region I'm going to work over. If I'm working in two variables, x and y, I'm going to have a two-dimensional region. Back in Calc 1, we were working with one variable x. We had this little part of the number line we were looking at here. But that's what we're doing. Those boundaries are creating this region of integration for us, which the book is going to refer to as R. Okay, so when we see just a capital R written like that, that's what it means here. So those boundaries aren't just numbers to plug in, they have meaning. And we don't really know what the inside represents now, so we don't really know what this is a region the region of integration of. It's just some region, but eventually we'll start putting meaning to this and it will mean something actually just in another. Okay, so when we do these problems, we'll try to go back and graph this most of the time. If we take those limits of integration and say, well, what do they look like? We should be able to create this two-dimensional region in every problem we work with. Okay. All right, so here's that stuff I was saying that seems like it is making something we already know just more complicated. And it kind of is, but there's a purpose to it. So just kind of bear with it for now. Hopefully we can understand a simple situation to apply it later. Back in chapter 7 of Calc 2, you talk about a lot of different uses of integrals. The very first one we talk about is find the area between two curves. And it's usually fairly simple. You're taking the integral from something to something of top curve minus bottom curve. That's pretty much it. So this is just a review problem, basically. So let's look at this as just review from chapter 7. We'll do it the same way we know. Find the area of the region bounded by, and we're given two functions, 4 functions, I guess, if you count the x's here. So let's graph it. What does this first function look like? 4 minus x squared?
4 minus x squared looks like
Parabola.
The parabola's been flipped upside down and then shifted up, so it looks kind of like this. And that would be a max at 4.
Yeah.
Similarly, y equals 2 minus x squared, also parabola, just not up quite as high, so it looks kind of like this. Okay, and you can graph this on something better if you want, but we're just sketching it here. If we think about those boundaries, if we have x equals -1, x equals +1, and this isn't very to scale here, so I apologize for not looking great, but x equals -1 is somewhere over here, and +1 is somewhere over here. And so what this is doing is saying, okay, we are trying to find the area of this region right here. Okay, do these problems look familiar?
Yeah.
These weren't super hard problems to do there, and that's not really going to change. We're just kind of use the idea here. So to find the area, we are going to integrate from what to what? What are our limits of integration?
-1 to 1.
Because again, those are the boundaries. That's where x is ranging from, -1 to 1. We're talking about this little portion of our number line right there. Okay, and then the integrand, what are we going to have over here?
4 minus x squared times or plus. I don't know how to go about it, but you add the other integrand.
We're not going to add the other one. We're going to subtract the other one.
Oh, yeah, you subtract.
Okay, because remember, the idea basically is if you think about finding the region underneath that whole blue curve, the 4 minus x squared is too big. And so we're kind of cutting off that little bottom piece, that white part that we don't care about, which is the 2 minus x squared. So we get this. Or you can think about it in terms of rectangles. The heights of all these rectangles are given that way, but we are going to subtract. and then dx. Okay. So we set that up. We go through and solve it. The point isn't really the solving things here. I'll just tell you the answer. You eventually get 4. Okay, that's not the point of going through this right now. It's the idea that we are taking these two curves and finding the difference between them. Okay, we're going to take top function, and then we're going to go back and subtract the bottom function. Okay. So does that look familiar? Right.
Yeah.
So what we're going to do now is we're going to say, okay, well, we're still going to stick with this same picture. We still have the same picture of top curve, bottom curve, just in a flat plane. We want to go through and find the area of this thing still. Well, this picture, despite being a bit more complicated, but it's kind of similar to what we did up here, right? I mean, it's still just a two-dimensional region. It's got boundaries in terms of x, boundaries in terms of y, just a little bit more complicated there. So what we're going to go back and do is set up basically the same thing that we have written right here, and that's going to go through and set up the area for us. Or maybe a better way of thinking about it, and I don't know if this is going to be clear either, but if we think about the fundamental theorem of calculus, it says we take the integrand, that after we integrate this thing, we're going to go back and plug in the top function or the top value, and then subtract again, we plug in the bottom value, right?
Mhm.
So essentially what we're going to do is we're going to say, okay, well, we have a difference in this integrand, and we will, every time we set up one of these problems, we've got essentially this top function and this bottom function, and we're always going to be subtracting them. So if we imagine kind of like backing up a step, if there was a step before this, which we've never seen before in Calc 2, but if there was a step before this, we could theoretically write this inside part as the answer to a different integral here. So we still have area, we still got the outside, that's all going to stay there. But instead of that inside being top function minus bottom function, if we imagine applying that fundamental theorem of calculus, okay, this should give us the same exact thing we have listed in the step above it, as long as the integrand is 1 and we treat that as a dy problem. So if you imagine this piece right here and going through and solving that, the solution to that little purple box is this right here. Does that make sense?
A little bit.
Yeah.
So go through and think about integrands. Leave the outside alone. If we were going to find the antiderivative of 1 with respect to y, what is it?
Is it 1?
Why?
It is just y. And if we're going to go back and evaluate that from the top integral or the top limit to the bottom limit, don't actually do the algebra. What do you get if you go through and just do a substitution? What are we going to have first here?
4 minus x squared.
X there.
Yeah, 4 minus x squared minus 2 minus x squared, right? Which is exactly the same thing as the integrand we have here. So again, this seems useless because why would you bother making it more complicated if we already know how to do it? But again, it's that idea that how are we setting up these integrals? How are we going to go through and do this? We're starting with a very easy case right now. The integrand is just 1, but this is kind of the idea. We're building this region. When we go back and look at those limits of integration, they are essentially just building this region right here. Oh, if my pen would work. Okay, that's all these limits are doing is telling us that shape there. Okay. Make a little bit of sense? Again, I know it seems weird, but a little bit of sense where the parts come from?
Yeah.
Okay, so that's how we're going to approach these iterated integrals. And I already wrote that over here. So for the example we just did, I already wrote it over there. So this is just the same thing. I'll write it here so the notes are filled in. Writing it backwards out. -1 to 1. Bottom function, top function. Okay, but that's the same thing we just wrote before. And that's going to be our first use of an iterated integral. We're going to have these two integrals together, and we're just going to write that in general terms. So anytime we're working with some region in a two-dimensional space, how can we go through and find the area using this two-integral process here? And that's really what this definition is giving here. All right, so it looks a little more complicated than it is. R just means we're working with that region in some two-dimensional plane. Is defined by x is between a and b, y is between some functions of x, and then we are given this integral right there. So that's just written out the definition of it. What is the integrand in this problem? What are we integrating? Yeah, I saw Stephanie say it, just 1, right? At least it looked like you said 1. Okay, so the integrand for this problem is just 1. We don't have to bother writing it because you guys know 1 times anything is just itself, so it doesn't change things here. Before we go on to the next one, because really the definition below that is the same thing, only your x and y is kind of a switch places here, but this kind of leads to another kind of little mini definition there. So think about the region this thing creates here. So if we consider that region that we're working with on this, it says that x is going to range from a to b. So just some constant to some constant. And on our x-axis, the outer limits are going to go from a to b. It then tells us that y is going to range from some function of x to some function of x. And we don't know what those look like, so just make up your favorite kind of functions, whatever. Okay, we're going to have some function g2, some function g1, a and b. And so what we're working with is the area of this little region in here. I don't want to draw lines. For the second one, oh, let's finish this first. We can call this a vertically simple region. And if we don't think too hard about the name for this, vertically simple basically means that our vertical cutoffs are very simple, or in this case, they are just straight lines here. So if we think about the edges of this shape, they are just vertical lines. Are the top and bottom cutoffs nice straight lines? I mean, I did draw a picture very well here, but the top and bottom cutoffs could be curves. Doesn't matter here, but we have these x limits are just constants. That's going to create this vertically simple region. And so that's why we kind of set it up, do y on the inside, dx on the outside. If we switch the order of integration, which is what this is looking over here, this is going to make a horizontally simple one. And I will still sketch a picture. But so if we follow the same idea that we had up there, we still got these two things, x and y. But now the difference is we have y on the outside. And so y is ranging from some constant to some constant, so from c to d. And then we've got our x on the inside. And so x is some function of y, who knows what it is. And then some other function of y. So we got like h2 and h1. And so the region that we're looking at in here is like this region over here. Are the left and right boundaries on this one just vertical lines?
No.
No, right. But now the top and bottom, where your horizontal boundaries are just horizontal lines. So that's what we mean when we say horizontally simple, is in a horizontally simple, our boundaries for y are the simple ones. They're just giving us horizontal lines. And then a vertically simple, our boundaries for x are the simple ones. And that's not going to be a super important vocab word to use, but that idea of thinking about that region, when we have something that's vertically simple, it's a lot easier to put x on the outside because your x constants are very easy to work with there. When we have something that's horizontally simple, it's a lot easier to put your y constants on the outside because y is a lot simpler to work with. So we can still set up the limits and go through the problem without remembering ever to say horizontally, vertically simple, but just kind of keep that picture in mind, that idea that sometimes in one direction it's going to be much easier than other directions there. Okay, we're still interested in finding the area. It's really all we're looking at now is find the area of these things, but just depending on the direction. And it is very similar back again to chapter 7. In chapter 7, you have the option to do problems as dy problem or dx problem, and that's really the same thing we're doing here. If you would do something as a dx problem, it's vertically simple. If you do something as a dy problem, it's horizontally simple. So it's a very similar relationship. We're just going to talk about iterated integrals. Questions?
Nope.
Okay, let's do another really easy one. Example 4, use an iterated integral to find the area bounded by the 4 equations, and then we're given some numbers. I would always start off by graphing the region. Okay, and almost every problem we do in this chapter, I think that's a good way to go back and do it. Start off by graphing that region there. All right, so x equals 2. It's just a vertical line. 1, 2. X equals 5, also a vertical line, so 3, 4, 5. And then similarly for y, got y equals 1, and y equals 7. 2, 3, 4, 5, 6, 7. Okay. So where are these guys all create that little region? That is our region R that we're trying to integrate over. What shape is this?
The rectangle,
How do you find the area of a rectangle?
9 times width.
And so for this guy, what is the length? Between 5 and 2, there's 3.
3.
And then from 1 to 7, there's 6. So the area is 18. So there's really no reason to do something more complicated with this one. Again, the answer itself is what we're going for, is kind of the idea. So there's the answer, right? If we want to find the area, we've got it. But to do it the most complicated way we can right now, to find an iterated integral for this, we're going to still go through and talk about setting that up there, okay? So don't really worry about this too much right now. Let's just remind you that in context, there's an easy way to do this. Is this region vertically simple?
Yeah.
Is this region horizontally simple?
Yeah.
So basically it's saying it doesn't matter if you do dx, dy, or dy, dx. They're both going to be pretty easy to go through and solve. It doesn't really matter here. So note that real quick. So pick your favorite. I'm going to leave spaces for our limits of integration. Let's just say dy dx. Okay, if you like the other way around, that's fine. It's not going to change things too much. To set up the iterated integral, we are always going to have integrand of 1, like Stephanie said before. So if we want to write that there, great. If not, that's still a-okay. And we just really need to go back and say, okay, well, what are the limits of integration? And so whether you want to work from the outside in or inside out, whatever makes more sense to you, but I will try to be consistent. So let's start off with the inside. So in terms of y, we want to know what are the limits of integration for this function. There it goes. So what does y range from?
1
Y
to
is from 1 to 7.
Radio. Okay, we can tell from the information up above, we can tell from looking at the graph, but we are saying if we're doing dy, then our inside limits have to be in terms of y. And then similarly, if we go for the outside limits, which is in terms of x, we're going to be outside limits.
2 and 5.
Mm-hmm. Okay, very easy problem to solve. I mean, there's just constants all over the place here. So if we integrate this real quick, just to verify that we indeed do get 18. Antiderivative 1 with respect to y.
1, I mean y.
Mm-hmm. I'm going to evaluate that from 1 to 7. So that is going to be, we still have the outer integral. That'll be 7 minus 1 to just 6. And then similarly, antiderivative of 6 with respect to x will give us 6x. We're going to evaluate that from 2 to 5. So there's a complicated way of getting the same answer we had before. Okay, so again, it's not really so much that we want to do this way to get the answer. It's just pick a simple example to talk about the setup with. Okay. And if we would have done this dx, dy, limits of integration would have flipped around, but we should still get the same answer in the end. Questions?
Yeah.
Okay, next one's a bit harder. It actually involves hopefully some more thinking here. Throw in some trig. Use the iterated integral to find the area bounded by f of x equals sine and g of x equals cosine. And we'll just talk about one section here. And I don't care what section, it should always be the same. So let's start off by graphing it like before. Sine function starts at 0. Pi over 2 we max out. At pi we are again at 0. 3 pi over 2. We're going to hit -1. And then 2 pi, we hit 0 again. So let's color code this. So the sine is going to look something like this. And then the cosine is not really the opposite of that, but the cosine follows different patterns. So from 1 to 0, -1, kind of like this. Okay. And when I say just one section, I mean we're just looking at one little place to overlap because we know these things go on and on forever. There's an infinite amount of little sections that they go through and create. Let's just say pick this one right here that we can see. And recall back in Calc 2, this is a fairly easy problem. This top function minus bottom function, you're going to need to know where these things intersect. We're just kind of taking it up a step from there. Is before we get to that setup, kind of where would that have come from if this was a double integral problem here? So here we go. I'm going to leave some space for my limits of integration. Integrand is just 1. And what order should we do this in? Should we do this as a dx, dy problem or dy, dx problem?
Does it really matter?
I don't know. It's a good question. Is this thing vertically simple? If you think about the cutoffs on the outside, are they vertically simple?
No.
How about horizontally?
No.
Yeah, heck no horizontally. I mean, horizontally, they're almost worse than they were vertically here. I'll tell you for this one, let's do this as dy, dx, and then we'll work through it that way. And then we'll briefly talk about if we flip the order around. Okay, so we're going to stick y on the inside, x on the outside. So for the inner limits of integration for y, we need to know what y is ranging from. And be careful here. This is the complicated part. This is where we're going to go back and account for the fact that we have curves and we have changes here. So what is y bounded by on the bottom of this shape?
-1.
It does hit a low of -1, but is it always -1? So like it's -1 right here, but is it -1 over here?
No.
No. Is it -1 over here?
No.
No. So what are those lower limits always coming from? They're based on a function. What function are they always coming from?
Cosine x.
And that's going to be our lower limit. Okay, so your inner limits are complicated. They're going to account for the curvature of your shape. They're going to account for the functions that are creating your region here. Our lower limit, the lower bound for this whole entire region, or basically the bottom function is cosine x, which means the top function, or the top bound, similarly is that sine of x. The top of this region is always being controlled by that sine of x function. So the same thing you can think about for finding those is like what you would do if you're working in chapter 7 stuff, top function, bottom function, is top bound and lower bound. What about our x values? What does x range from?
0 to 2 pi.
Not quite. We need to, and I probably should have went back and found these cutoffs before.
Is it the opposite?
Pi over 4.
Mhm.
Cosine and, sine on the lower and cosine on the upper?
No, they're going to be constants on the outside. So your outer limits are always going to be constants. They have to just be number and number. Go back. Caleb's almost there. 5 pi over 4 is the other number you should come up with, CJ.
Think of joking.
Okay, so there's a setup, and let's explain why that is, right? Your outer limits always have to be constants. Okay, so x is our outer variable. Its limits have to be constants here. And the idea is similar. We're looking at, well, what does this range from? This goes from this point on the number line to this point on the number line. What are those values of x? They range from pi over 4 to 5 pi over 4. Those are the limits of integration. We also have to go back and do something else here too. We need to make sure that whatever limits of integration we're using for the inside function, don't use that variable. So our inside integrals in terms of y. Our limits of integration cannot have a y in them. Once we go through and evaluate that, y is basically gone from this problem. So when we work through and solve this in a minute, we'll see y is going to go away. But when we think about our outer limits, so when we go out to this x over here, we've got to make sure that these limits of integration don't have any x in them, and also don't have any y's in them. So we're always going to keep removing variables. As we move out further and further and further, we're going to try and knock out the number of variables that we're working with. Okay. So here's the setup, and let's work through solving it, and maybe that'll make a little more sense what I mean by knocking out variables. So leave that outer integral there. We're not going to do anything with that yet. We're following order of operations. Do the inside one first. And like we said a few times, antiderivative of 1 respect to y is y. Our limits of integration are quite a bit more complicated than just numbers, but they are still constants in terms of y, because in terms of y, cosine x is just constant, and in terms of y, sine of x is just constant, so they're okay. So if we go back and plug those in, we're going to have sine of x minus cosine of x. And if you pause there, that's that integral you would have set up in Calc 2. So we're really just doing more work than we were doing before. But again, there's a reason for this. It's not just crazy. There's a reason why we go through and do it this way. Okay. So we have upper limit minus lower limit, or top function minus bottom function. And then you can see now, are there any y's left in this problem?
No.
No, they are totally gone. So we do not want to re-put them in there with our limits of integration again. If we would have done what you suggested by flipping your sines and cosines at this point, we'd have y back in our problem. We don't want that. We want a number in the end when we're finished off with this. So the rest of this is just basically Calc 1 problem. Antiderivative sine is going to be negative cosine. Antiderivative cosine is sine. And we're going to go back and evaluate from pi over 4 to 5 pi over 4. And you guys can go back and do that substitution and evaluating points. You're eventually going to get 2 times square root of 2. So we got a more complicated way of doing something we did back in chapter 7. Oh, we are totally out of time. All right, so on Monday, I'll talk about what happens if we switch limits of integration on this, how that kind of affects the problem, and then we'll just work through these next few examples. Even though I said the homework for this is available, focus on your tests. Make sure you get your chapter 13 test taken care of if you haven't already done so, and then the homework for this will work on next week. Okay? All right.
Previous page.
What was that?
Can you go back to the previous page?
Yep. Do you need the bottom part?
Yeah. Yes, please.
Is that big enough to see or is that too small?
A little more bigger. All right. Thank you.
No problem. All right, have a great weekend, guys.
Thank you. All right. Thank you, Mr. Cole.
No problem.
Have a good weekend.
You too.
Thank you. What the heck did I just do? Look at this. Make it work.